Let's take a look at an example. It should clarify the process. All right, so we have a matrix A. It's a 2 by 2 matrix. We want to first find the eigenvalues of A. Then once we do, we want to take each one of those eigenvalues and find the basis for the eigenspace associated with each eigenvalue. All right, so let's first talk about finding the eigenvalues of A. To do that, we want to solve the characteristic equation. So as a reminder, we know we want our eigenvalues and our eigenvectors to satisfy this equation. If we subtract lambda x to the other side of the equation, throw in the identity matrix to make it so we can factor out x, factor out the x, then having our eigenvalue and eigenvector pairs satisfy this equation is the same as asking them to satisfy this equation. We use the fact that x cannot be the zero vector to realize that this homogeneous system must have infinitely many solutions. And the only way that happens with the square matrix is if the matrix is singular. Okay, not invertible. Which means we want to solve the determinant of A minus lambda I equals 0. The only time a matrix is going to be singular, not invertible, is when its determinant is equal to 0. This is the characteristic equation. If we can solve this for lambda, then we know the eigenvalues of the matrix. Okay? So in this case, matrix A is -1, -3, -1, 1. So we want the determinant of, what was it? -1, -3, -1, 1. And we want to subtract lambda times I. So that means I will just have multiply the ones down the main diagonal of the identity matrix by lambda, zeros everywhere else. Okay, do the matrix subtraction. I'm going to get -1 minus lambda, -3, -1, 1 minus lambda equals to 0. Okay, so we have some variables in here now. We have lambda. We want to know what values of lambda make this equation true. Let's go ahead and take the determinant now. We know how to take the determinant of a 2 by 2. Start by multiplying these two. So that's going to be -1 minus lambda times 1 minus lambda. And then subtract what I get when I multiply these two. So that's -3 times -1. That's a +3. So I'm going to subtract a +3. And so I get a polynomial equation. We know how to solve polynomial equations, especially when they're equal to 0. The first thing I want to do is I want to multiply things out here. Okay, so if I FOIL things out, I'll get -1 plus lambda minus lambda. Those will cancel, right? Let me write it out just since it's our first time. Plus lambda minus lambda plus lambda squared minus 3 equals 0. Okay, so that means I get lambda squared minus 4 equals 0 once I combine all like terms, once I cancel these guys out. Now there's a couple ways to solve an equation like this. I'll do it both ways. Perhaps the easier way is just to first solve for lambda squared and then take the square root of both sides, remembering that we want all possible square roots, the positive and the negative. So lambda could be 2 or -2. Okay. The other way is to solve by factoring, and sometimes, a lot of times, solving by factoring is the only way. I notice this is a difference of squares. Lambda squared minus 2 squared. So I could factor this as lambda plus 2 times lambda minus 2 equals 0. The only way I can multiply two things together to get 0 is if one of those two things is 0. So either lambda plus 2 equals 0, in which case lambda equals -2, or the other way I could make this work is if lambda minus 2 equals 0, in which case lambda equals +2, okay? Both methods give me the same answer, right? The two eigenvalues of this matrix are +2 and -2. So eigenvalues of A are lambda equals 2 and -2. All right? So we found the eigenvalues by using the characteristic equation, by solving for the variable in the characteristic equation. Okay? Now what I want to do is I want to go back to the homogeneous equation here. I'm going to take each of my eigenvalues in turn, I'm going to plug them in, and then I'm going to solve the resulting equation. Okay? So let's do 2 first. So for lambda equals 2, I'm going to get A minus 2i, no, 2i times x equals the 0 vector. Okay? So A minus 2i, A is matrix -1, -3, -1, 1. And then minus 2 times I, I'm just going to multiply scalar 2 times the identity matrix. That just gives me 2 down the main diagonal, zeros everywhere else. And if I do the matrix subtraction, I get -1 minus 2 is -3, -3, and then -1, and then 1 minus 2 is -1. Okay, what we want to do is we want to solve this equation. All solutions to this equation, every x that makes this equation true, is an eigenvector for lambda equals 2. Okay, so to solve a system like this, we are going to put it in augmented matrix form. I'm going to leave the 0 on the augmented part out as usual, and then we just want to find the reduced row echelon form of this. Now this one's simple enough that we could probably do it in our head, but we'll be lazy about it. We'll get our calculators out. Okay, so I've already run this code cell. Let's add another one. Let's add our matrix. I'll call it M. I want to be a little careful about calling it A because A was our original matrix, -1, -3, -1, 1. This matrix is -3, -3, -1, -1. Okay, and there it is in reduced row echelon form, 1, 1, 0, 0. Okay, notice that we do not have a leading entry in every column, right? This column has a leading entry, this one right here, but this column does not. This is not a leading entry. It's not the first non-zero entry in the row. So there is no leading entry. That means for the system, it will correspond to a free variable. That's good. That's what I want. If I don't have a free variable in this after I've done the reduced row echelon form, then I've done something wrong, right? We have chosen the values lambda to make sure that our system here will have infinitely many solutions. We'll have at least one free variable, okay? So our eigenvectors are going to be a solution to the system, so I can use this matrix here to tell me what our solution is going to be. The augmented part, you can imagine the zeros here, right? And so x2, or yeah, our second variable is going to be our free variable. So let's say x2 equals t. And then looking at the first equation here, we would get 1x1 plus 1x2 equals 0. Okay, swap out x2 for the free variable t, and I see that x1 is going to be negative t. And so my general solution, x1, x2, is going to be t, negative 1, 1. All right. Every vector of this form is an eigenvector of matrix A with associated eigenvalue lambda equals 2. Okay. Now, the original problem didn't ask us to find the whole eigenspace. It asked us to find a basis for the eigenspace. And we can see here that negative 1, 1 is a basis, right? Any linear combination of this vector is an eigenvector for the system, is a solution to this homogeneous system. So S lambda S sub 2, the eigenspace associated with eigenvalue 2, is equal to all vectors that can be written in this form, which means it's just going to be the span of vector negative 1, 1. That's its basis. Okay. Okay, so we've done one of our two eigenvalues. We found the associated eigenspace. We found a basis for the eigenspace, but we still have one extra eigenvalue to look at. All right. So let's do this for lambda equals negative 2. We're going to do the exact same thing. Okay. We're going to look at the homogeneous equation, a minus lambda I, but we're going to plug in negative 2 for lambda. And we're going to solve the homogeneous system. So matrix A is negative 1, negative 3, negative 1, 1. Negative 2 times I is negative 2 down the main diagonal, zeros everywhere else. And so if I do the matrix subtraction, negative 1 minus 2, that's what? Negative 1 plus 2, that's 1. Negative 3, negative 1, and then 1 minus negative 2 is 3. And hopefully you've done this enough times that you recognize, okay, these columns are linearly dependent, right? They're scalar multiples of each other. So once I find the reducer echelon form of the matrix, I'll get a free variable, which is what I want. Okay. So let's find the reducer echelon form. Pull up my calculator again. I'll use n, maybe I'll use n. 1, negative 3 is the first row, negative 1, 3 is the second row. And I want to find the reducer echelon form of this matrix. And I get 1, negative 3, 0, 0. One, negative 3, 0, 0. So that's the reducer echelon form of this matrix. Just put a bar here to separate the two halves of the problem. Now I need to use this to solve the homogeneous system. Remember, we imagined 0, 0 as being the augmented part. I do have a free variable. x2 would be my free variable. So let's assign x2 to be t. And then row 1 tells me 1x1 minus 3x2 will be equal to the augmented part 0. And so swapping out x2 for t and solving for x1, I get x1 equals 3t. And so my solution here is all vectors that can be expressed as t times 3, 1. Some scalar multiple of vector 3, 1. So the eigenspace associated with eigenvalue -2 is equal to all vectors that can be written in this form. For any real number t. Okay? Every vector in this space is an eigenvector of the eigenvalue -2. Okay, so that's the eigenspace. We could see that every vector here can be written as a linear combination of this vector. So our basis for this eigenspace is going to be just vector 3, 1.